Which of the following statements is true about the function f of x equals 1 over x squared as x approaches 0? Well, we do know, that's me trying to draw a straight line, we do know that 1 over x squared is going to look like this. Okay, this is the parent rational function. You should know that. Okay, as x approaches 0, well, if the limit as x approaches 0 is what we're being asked, the limit doesn't exist. Why? Because you're going up at 0, you're going down at 0. They don't match up. The left-handed and the right-sided limits don't match up, so the limit does not exist. The function has a horizontal asymptote at y equals 0. That actually is true, so we could circle it. The limit as x approaches 0 is infinity. No, it doesn't exist. The limit as x approaches 0 is negative infinity. No, it doesn't exist. The function is continuous at 0. No, that doesn't make sense because if I plug in 0, I get 1 over 0. So right off the bat, we had our correct answer. Nothing crazy. Makes sense to me. Boy, was that fun. Evaluate the limit as x approaches infinity of 5x over x plus 2. If you're in AP Calculus here in 2024, you probably took AP Pre-Calculus, so you should be familiar with this. Whenever you take the limit as x approaches infinity of a polynomial over a polynomial, what you do is you circle the leading term in the numerator, you circle the leading term in the denominator, and you simplify just those guys. I don't care about anything else. 5x over x. 5x over x crosses out, and you're left with 5. So now this is me air quoting plugging in infinity. Well, there's nothing to plug in if there's no longer an x. So since there's nothing to plug in, 5 is left over. So when the degree in the numerator is the same as the degree in the denominator, and I'm taking the limit as x approaches infinity, or negative infinity, it's just going to be whatever the leading coefficient over the leading coefficient is. And so I have 5 over negative 1, which is 5. My answer is A. Compare the relative magnitudes of the functions as x approaches infinity. For f of x, we have x to the third power, and g of x, we have e to the x power. This is a cubic. That grows fast. This is exponential. That grows 1,000 times faster. Exponential, anything to the x power, whether it's e or x, is going to grow a lot faster than x to the any number. So e to the x is going to grow faster, or in this case, g of x is going to grow faster as x approaches infinity. So f of x grows faster than g of x as x approaches infinity? No. G of x grows faster than f of x as x approaches infinity? Yup. Both of them grow at the same rate? Nope. F of x approaches a horizontal? Nah, I'm not even going to bother. Okay, so since this is exponential to the x, that's going to grow at an exponential rate. That is cubic, not near as fast as g. Evaluate the limit. The limit as x approaches infinity of ln of x over x. Whenever we have an x over an x and we're dealing with infinities, the last thing you want to do is quote-unquote plug in infinity, because then you'll get infinity over infinity. So what you need to do is consider the magnitude. Which of these is going to grow faster? Well, the graph of ln of x looks like this, and it's going to flatten out as x approaches infinity. The graph of x is going to continue increasing at a constant and steady rate. So what's going to happen is the denominator is going to grow faster. So the denominator is going to approach infinity a whole lot faster than this guy does as x approaches infinity. And when the denominator approaches infinity faster than the numerator, you have a limit that equals 0. So in this case, the limit as x approaches infinity of a slow-moving graph over a regular moving graph is going to be 0. A is going to be my guy. Evaluate the limit as x approaches infinity of x to the fourth plus 9x squared minus 10 over x to the third minus 8. If you took AP Pre-Calculus, you already know that if you're given the limit as x approaches infinity, you care about the leading coefficient over the leading coefficient, rather the leading term over the leading term. And we only care about those. We don't care about anything else. And so when you focus on those and say, all right, x to the fourth over x to the third simplifies to regular x. Now I can plug in infinity, and when you plug in infinity, you get infinity. So you might remember from AP Pre-Calculus that if you have a polynomial with a higher degree in the numerator than a polynomial with a smaller degree, if it approaches infinity or negative infinity, your answer is going to be that infinity as long as you have, whatever symbol you need. What is the range of the following function? You have f of x equals the absolute value of 5 sine 2x. All right, well, I only care about the range. Now, this is me graphing regular 5 sine 2x. Okay, 5 is the amplitude, goes up to 5, goes down to negative 5. Sine of 2x gives me a period of 2, so it kind of squeezes things in. Not that it matters, but it's going to look like that, look like that, look like that. Well, since I'm being asked to find the absolute value of it, this purple graph is going to be the only one that matters. So it still starts out up here, but since it's an absolute value, it's got to stay positive. So it's going to bounce, and then bounce, and then bounce, and so on and so forth. So basically, my purple answer is going to be the guy that matters here. And my range is going to be everything from 0 to 5, and including both of those. So we will say 0 is less than or equal to 5, which is less than or 0 is less than or equal to y, which is less than or equal to 5. That's going to be my range. Kind of a strange calculus problem, but I liked it, and so I kept it in here. Baby.